All right, good afternoon, everybody. Welcome to Electrical Trends, the Path to Sustainability. My name is Roger, and I'm going to be having a conversation with you, I hope, for the next 2 hours. And you know what I said, having a conversation, which means this is an interactive webinar. And so let's just establish a couple guidelines here. The easiest way with a group this size to get questions and answers back and forth is for you to type your question into the Q&A. When you do that, my screen flashes at me and says, hey, there's a question. If you have any administrative kinds of issues that you want to, sound problem, video problem, whatever, please contact the host by way of the chat box on that. Okay, so for questions and answers, we'll use the Q&A box and the chat box for the host, okay? Let me apologize at the outset. I'm hoping not to be coughing too much, but I still have some residual COVID coughing here from a few weeks ago. But if I can just ignore it, maybe it will go away because we've got better things to talk about. All right, let's get started here. This probably isn't surprising to anybody, but things are a little different now than they used to be. Cars a little different, and transportation systems, and there's a few other things that we just don't see very much of anymore. Although that 30XA I use on a daily basis, but it's kind of old. I don't use my slide rule anymore, and don't see too many of these kerosene lamps out there anymore either. So in any case, yeah, things are changing, and I think the comment that's appropriate here is that we ain't seen nothing yet, because we're going to see some significant changes, I think, over the next 10 years. And this 79-year-old guy is looking forward to hanging around to see some of those take place, to see whether predictions we're going to make today actually come true. So let's have a look at how we use generate. You've seen these pictures of nice clean electricity. At least that's the way we used to do it. We've got a few new ways to do it. The wind machines seem to be, they don't give off a whole lot of smoke. Sometimes they're a little noisy if they make a lot of turn around really fast, but not so noisy that they're really disturbing. So, and as a result, a lot of these are being installed. And then there's the solar part, and make electricity with solar. And of course, there are a number of other things out there that are more regionally specific, things like hydroelectric, things like geothermal, and so forth. But the solar is pretty much usable everywhere. And the wind is well, there are certain areas that are a whole lot better for wind power than others. So wind doesn't have quite the same appeal. I don't see very many windmills like this in people's backyards down in my neighborhood here in South Florida. But if you drive along Highway 2 in northern Massachusetts, you'll see wind farms like this. So they're out there. And so we're going to talk about some of these changes and how they're going to affect the way we all do business as engineers and architects, and what the opportunities are and what the benefits of these are in terms of cost benefit and a few other things. So let's take a look at what some of the trends are. We're have been moving from inefficient to efficient for a long time. We've been moving from fossil to renewable for a while. Maybe we've been moving pretty significantly over the last 10 years or so. But we had to learn how to do it, and that took a little practice over about 30 or 40 years before the last 10 years. But it is happening, and we'll see some of the results. Nobody's ever claimed that solar or wind energy was very dirty, and there's not much smoke, so we're moving from dirty to clean. That so far so good. Sounds like some pretty good changes here. On the other hand, we're moving from predictable to less predictable sources, and that's something we're going to need to deal with. a cloud comes over the sun and all of a sudden your solar system isn't making as much electricity as it was 2 minutes ago. And of course, at night, it's predictable that your solar system is not going to be making any electricity, so we need to make provisions to cover that. So we're going to talk a little bit about how we need to do that. We've had some energy storage for quite a while, 50, 60 years or so, because once upon a time, when they first started up nuclear plants, they discovered that it is they're very touchy for adjusting. And once you get them running the way you want them to, you don't want to mess with the dials. So therefore, they found that when they had excess electricity at night, they wanted to find something to do with it. So they started pumping water uphill, and thus became the advent of pumped hydro storage a long time ago. And that came on because of nuclear at night. Now we're able to use pumped hydro storage to pump excess solar or wind energy during the day as well. So our pumped hydro is becoming even more useful. More high voltage DC transmission lines are being built in the United States and in other places around the world. Chinese have been building some big ones. So it's something that's happening. If you're in the in the utility business, your company may very well be considering some if you're trying to move electricity for a distance more than 300 miles or so. And there's a whole lot more control and data analysis going on in order to make these systems efficient. So let's look at some solar just for a little while, photovoltaics, because it gives us an idea of what has been moving this movement. If you look at the cost, in 1975, the cost of solar modules was over $100 a watt, whereas in 2015, it was down below $1 a watt. And I can remember back in the year 2000 when folks were saying we'll never get below $1 a watt because it costs that much for the frame and the glass. Forget about the the silicon part and the active part. Well, guess what? Look what happened in 2012. We got below $1 a watt. The big thing that changed was a major breakthrough in refining and purification of silicon, as you can see there in 2008. And given the processes required a whole lot less energy to produce good solar grade silicon, and the cost has been dropping pretty rapidly ever since. And notice that's a logarithmic scale we're looking at over there on the left, not a linear scale. So in 2020, cost was about 30 cents a watt for the solar. And of course, that depends on what module you're buying. Some are more expensive. Some of those that we use in the 175 mile an hour wind zone down here in a place like Miami Beach, they're a bit more than 30 cents a watt to make sure they're strong enough to not blow away. But up in the lower wind zones, some of the, and for large quantities, 30 cents a watt is not an unusual purchase price for the installers. So let's take a look at what's happening with photovoltaic shipments, and what's happening is that you're selling a whole lot more of them. And you see that this chart I first drew in 2014. And it was moving up kind of exponentially. As you can see, we're looking at, again, a logarithmic scale on the left-hand side. So the question was, where was it going to go from 2014? Well, 2016, it went up a bit. And here it is in 2021, up into the 100,000 megawatt range of shipment. And that's a per year thing. Okay, annual shipments of over 100,000 watts of photovoltaics, or 100,000 megawatts. That's a lot of solar. I mean, that's not just playing games. So installations have come down. In 2021, residential installation was around $3 a watt. Again, depends on the installation itself, but that's a good average for thousands of installations. And utility costs have come down to $1 a watt by 2021. So the only thing about utility is those are very large fields that are out there, ground mounted systems. And sometimes people get upset about using that property, and that's all between people who want to build these things and the local zoning people. So presumably that gets resolved in a democratic and equitable process. I see a Q&A up here. I'm going to take a look here, see what we got. Where is PV primarily developed? There's a lot of PV developed in China, but there's a lot of it developed in the Philippines, in the United States. That's a fairly important photovoltaic business going on. Actually, one of the participants in this webinar might be able to type something into the Q&A. Mindy, do you remember some of the, I don't remember all the places the manufactured some of the newer modules that we've been seeing. But China has a significant number, and they are installing a whole lot as well. So China is part of the equation here. Yeah, Jinko, for example, in North Carolina, the United States. Thanks, Mindy. And that there's somebody down in Louisiana, if I'm not mistaken, too, who somebody who builds a pretty good panel down there. I can't be speculating at this point, but in any case, the number of places where these solar modules are being manufactured is getting, there's more of them every year. And it's not just China and the United States anymore, or Germany, but all of them are part of the total picture. Okay, so here we are in 2021 in terms of this is manufactured and shipped to be installed. And the prices are down there at $3 a watt. Well, let's take a look here. And this, by the way, $3 a watt is before the investment tax credit, which is now at 30%. So that makes quite a difference as well. Here's a few numbers coming up where solar is being installed. This happens to be a 10,000 watt system battery backup down in Florida that's at a school that serves as a hurricane shelter electrical backup system. These were installed about 10 to 12 years ago. And some of the numbers here, I'm sorry, I thought that had left my throat. Okay, so in the United States, in 2020, 3.1 gigawatts of residential systems were installed, and 16.57 total gigawatts was installed in the United States. So as you can see, 3.1 out of 16.57 is only about 20% residential, and the other 80% is commercial and utility here in the United States. In 2020, globally, yeah, I am so sorry, folks. I did not expect my throat to do this afternoon. In 2020, the global added PV capacity exceeded 107 gigawatts. So the United States only accounts for about 17 of 107, and the rest of the world. So in other words, the message here is the United States is not the only country in the world that is getting heavily into PV. There are others who are doing about 80% of the job, and maybe here in the United States we're somewhere around 20%. China, for example, installed 48.2 gigawatts of this 107. India installations dropped because of the pandemic, but they're going up again very quickly in India. But in 2020, it dropped down to 3.2 gigawatts. There were 317,000 solar industry jobs in the United States in 2020. The efficiencies of PV modules continue to improve. The reliability continues to improve. Believe it or not, research on and competition is amazingly good for this kind of thing to happen. And the costs continue to decline. And that this is not just the modules, but the electronics, the installation. Most of the factors entering into the cost of installing a system are still going down. So what about the wind? Oops, here's a couple more questions. Let's take a quick look here. Oh, okay. Just noting that Jinko Solar has a factory in Jacksonville, Florida, as well as in Malaysia and Vietnam. Okay, and thank you. If anyone else has any, I'm not the only guy who has answers here. Everybody in the audience may well have some answers. So I encourage you, if you see a question in the chat, and if you know the answer, don't hesitate to type it in. That's fine. I have pride of being able to accept other people's answers. Okay, wait a minute, I forgot to click at these things here. All right, that makes it easier for me to keep track of them. Okay, so what about the wind? Well, 85,000 people employed in the United States in 2022 building wind machines. That's from the U.S. Bureau of, I knew what the BLS was. Bureau of Land, don't remember. Anyway, you can always Google US BLS to ask what that is. Okay, and worldwide, 97.5 gigawatts of wind power was installed in 2021, 840 gigawatts of worldwide cumulative total in 2021. Okay, you can compare that with the cumulative total of PV on this slide when you look back at that one. And in addition to this 840 gigawatts of large turbines, there were another 945,000 small wind turbines back in 2014. I have not been able to find an update for this number. I've looked around, tried to find it, but they had a total capacity back in 2014 of 830 megawatts. So there's quite a lot of wind out there as well. And a large wind turbine can generate almost 2,300 kilowatt hours per kilowatt per year. So for every 1,000 watts of wind, you can count on it to generate close to 2,300 kilowatt hours a year. And if you want to do that with PV, you can do that with solar in the desert, but in most other locations, you can pretty much count on PV to generate somewhere in the neighborhood of 1,500 kilowatt hours per year per kilowatt. Construction for wind has been around $1.50 to $2 a watt. But we have to remember the best performance requires sustained winds. Another Q&A. Oh, U.S. Bureau of Labor Statistics. Of course, how can I miss that? Thank you, Edward. Thank you very much. I appreciate that. And I knew that 2 days ago, but I'm at a point where sometimes I just get these mental blocks. I'm sure nobody else in the audience ever gets any, but I may be getting enough to make up for everybody else. Okay. The thing about, solar is linearly dependent on the intensity of sunlight, the amount of power you get out of your solar system. Whereas in wind, you got to realize that the force involved is proportional to the square of the wind velocity. And then the power is, of course, force times velocity. So we're getting into a cube. And not only that, we're transferring a linear velocity into a rotational velocity when the wind hits those blades. So we're almost looking at the cube. So that's why this cubic relationship, as opposed to a linear relationship, makes the sighting of wind a little more complicated. Not that folks haven't figured out where it is. And those who are in the wind business, they are out there, they are testing to make sure that the wind is blowing the way they think. And at the same time, they are designing systems. Here's some worldwide growth in wind power from 2014 through 2021. We're looking at 825 gigawatts in 2021. So from 370 to 825. from in 7 years. That's pretty significant growth. Okay. Where is it going? Well, guess what we've got it. China has 329 of these 800 some odd gigawatts. The European Union has 187. The United States is down at 133. So Chinese love those wind machines. And at that point, it drops off relatively quickly as you go through United Kingdom, Brazil, France, Canada. And the United States is only number 3 in wind power. The European Union has been into wind power for a lot longer because electricity has been more expensive over there, harder to generate. So wind became cost effective there quicker, earlier than it did in the United States. So now we already talked about this. So let's talk about this little picture here. I'm just trying to present some background here, folks, so that we have an idea of where we've been and where we're going. And then we're going to get into some more specifics as to, as we go, how do we do some of this stuff? And we're going to spend a bit of time on, for example, on designing electric vehicle charging. Question here, my stats include offshore wind. My understanding is that this wind is onshore and offshore. Offshore wind is more expensive than onshore wind, but I think this includes everything, all wind machines that are greater than a megawatt. I think that is where the stats come in. So now the question is, here we are in 2022. As of 2019 and 2020, you can see that the 3 fossil sources were right on up there with 100 quads or more, up to 200 quads for both the petroleum, the coal, and the natural gas. Notice what's happening, though. Notice that the natural gas is going up, the coal it's bouncing around a little bit. The natural gas has been going up, and the crude oil has been going up until 2019. And then in 2020, it seemed to level off a little bit. And I don't have the data yet for 2021 and 2022, but it's anybody's guess where these things might go. But the green one is the one that's really interesting. That's the renewables, and that's renewables other than hydro. All right, so that means solar, wind, geothermal, and any other renewable source, any other source of energy classified as renewable. The dominant sources here at this point, though, are solar and wind. These have been increasing exponentially since almost day one, as you can see from the relatively straight line through the stars. And they still are. So the interesting thing is, if we can continue to do this, by around 2028 or so, they should, in fact, we're somewhere in the 2025 region, as the renewables get up close to that 100 quad mark, they're going to start eating into the market share of the fossil fuels. And by 2029, who knows where we're going to be by 2034. But if we play our cards right, it all depends on whose definition of right might be used, it would be possible to replace essentially all of the fossil fuel sources by 2035. Will it happen? Well, who knows? Maybe it just kind of depends on how important people think that is. And it is certainly going to depend a lot on the economics. The Europeans are experiencing extremely high fossil fuel prices right now. So therefore, the wind and the solar are looking very attractive to them. And of course, we can't leave out other important things like energy efficiency. So anyway, this is energy production in kilowatt hours, okay? Actually, it's in quads, but you can convert kilowatt hours to quads. And it's very interesting that in 2019, the renewable energy actually exceeded the nuclear kilowatt hour production worldwide, and it's been ahead ever since. So that's interesting, just plain interesting. And again, it's the economics of it. Nobody argues about nuclear being clean, but fixing the old plants is okay, but trying to build a new one is very expensive. So here's some the quads of consumption, just to put some numbers on the graph here. So again, I'd like to give you these numbers because if you download the slides, then you're going to have these to use, for example, tonight at dinner time conversation, but especially at Thanksgiving. Uncle Joe is going to appreciate hearing about this stuff so much that he'll probably forget to put the cranberries on the turkey. All right, so let's see, another question. Oh, a quad, that means a quintillion BTUs, 10 to the 15 BTUs. All right, and you can easily Google how many kilowatt hours are in a quad and how many BTU. Well, we know that how many BTUs are in a quad. So yeah, it's a huge amount of energy, the bottom line. Okay. And I'm glad you asked that question, because we tend to figure everybody knows what a quad is, and that's not necessarily the case. There's some very interesting units of like million barrels of oil, and just the energy industry has different ways of expressing large quantities of energy, and we just don't have a whole lot of time for discussion on all. I mean, we're going to use up this 2 hours. It's going to go by so fast, and it'd be nice to just have all this stuff. Generally, energy production equates to energy need, because the energy producers know, again, the economics, if they produce too much, then the price goes down and it's not a good deal for them. And if they produce too little, the price goes up too much and then people quit using it, and that's not such a good deal. So they tend to have agreements on production. That's what OPEC is all about. For example, they when they decided to cut on production back in the late 1970s, we found out what that did. So yeah, that was a so in any case, in general, energy production equates to energy need. Well, maybe need, that's an interesting word, maybe needs to be in quotation marks, because whether we need it or we want it or we use it or whatever, it might be better to say, does energy production equate to energy sales? Because that's really kind of what it's all about in a world of economics. I appreciate all the questions. A lot of good questions today, more than usual. And I may have to try to get through them kind of quickly in order to make sure we don't lose out on too much at the end of the presentation here, which some of which is pretty interesting. I like to think the whole thing is interesting, but that's for you to judge. Okay, let's move on. LCOE means levelized cost of energy. See, I got that acronym. And if we compare the levelized cost of energy among various sources in cents per kilowatt hour, here's the kind of things we get. And what does LCOE mean? This is the lifetime. If you develop a natural gas electricity generating facility and maintain that facility and provide it with fuel and take care of all the other auxiliary functions required with natural gas, and then take into account the decommissioning costs as well, you would have to sell your electricity for 5.6 cents a kilowatt hour in order to pay for that natural gas over its lifetime. All right. So this gives a very nice, interesting way. The only thing that's missing in LCOE is an environmental cost, which a lot of folks are feeling that ought to be cranked in as well. But for the moment, the environmental costs are not included in the levelized cost of energy. All right, but we got 5.6 on natural gas. But if we want to build a brand new nuclear plant, it's looking more like 11.8 cents a kilowatt hour. And onshore wind, about 4.1 cents a kilowatt hour. Photovoltaics, about 4 cents a kilowatt hour. Hydro, 6.4. We'll see what that asterisk is talking about. That's just from an earlier that was back in 2019, or DOE, that was back in 2017. Okay, so now the PV at 4 cents, from what we saw earlier, that's kind of averaging it out amongst the smaller systems and the larger systems. And so it depends on the assumptions that are made when you look at these numbers. Natural gas, for example, assumes that the plant is being run at a certain fractional capacity. So if it's capable of, say, 100 units of energy production in a day, and are we assuming it's going to run at 90, 80, 70, 60? And that's going to be different for every plant out there. So that's why these numbers vary a little bit depending on where you look them up. So just want you to realize that these numbers, if you look them up in different places, you may find some slightly different numbers. And that's the reason, is because they have to assume what percentage of the available production are you going to actually take advantage of. Like a peaking plant, for example, a power plant that you only run 5% of the time. That turns out to be very expensive electricity, up in the maybe 30 cents a kilowatt hour range. So just need to look at all these numbers when we're comparing what the options are. So what's happening on the grid? Well, we got a lot of EVs coming in, and they come in the form of all electric or plug-in hybrids. Energy efficiency, some very interesting stuff that's going on with almost everything. And we're going to look at, these are things we're going to be looking at from here on out now to see what can we expect to see, and where do we all fit into this big picture. Zero energy buildings, we're going to take a look at what they are, how they're defined, and whether they're cost effective. Distributed generation, energy storage, in other words, rooftop solar with relatively small storage, but then we can expect some very large energy storage as well. And folks have sat down and calculated exactly how much we're going to need in order to have a nice stable grid by 2050. So folks are busy doing a lot of research, a lot of development, and at some point or other, these things become cost effective, and that's when they start hitting the market and being a part of the total mix. So let's chat about electric vehicles for a little while, because I see electric vehicles as going to be an amazing effect on the grid, and an amazing effect on fossil fuels, and just amazing effects. We happen to own a plug-in hybrid. We have not put any gasoline in that plug-in hybrid since last May, and the tank is still almost full. So depending on how you drive your electric vehicle, and when I look out and drive along the road, I see a lot of Teslas and a lot of other EVs out there. So, and then there's the Norwegians who are mandating that by 2025 that EVs are the only thing going to be sold over there. So, and we're going to find out that, gosh, electric vehicles are cheaper to maintain, and the life cycle cost, or the LCOE, whatever way you want to describe them, is actually probably lower for electric vehicles. Very interesting. And we're extremely happy with ours. So let's talk about them. There's a lot of different kinds. My favorite one, of course, is this one in the upper right-hand side, but then there's the $150,000 that we'd have to come up with to own one of those, or sell our house or something and live in the car. But the one in the lower left there, that happens to be the one we're driving. That's a Honda, and that's affordable. And I really like that cute little BMW down there, lower right. If you're up in Long Island, you probably see a lot of those driving around, because the utility had an incentive program for those a few years back. And that Toyota is another electric, either plug-in or straight electric. So interesting stuff, and let's talk about them. And let's do some numbers, because after all, we've got a bunch of engineers and architects here, and without seeing numbers, people will not go home happy. So here are some numbers, okay? The range of electric vehicles is generally between 100 and 400 miles. Battery storage capacity, usually somewhere in the 30 kilowatt hour to 100 kilowatt hour range for the pure electrics. Most of the batteries are lithium based, and charging time depends on the charging level. So we're going to talk about that for a while, because some of you might be designing lots and lots of electric vehicle charging stations one of these days. Some of you might be already doing it, for all I know. Could very well be the case. Then there's a plug-in hybrid, and it simply has a larger battery pack than the typical hybrid, and you can plug it in overnight and get yourself maybe enough miles for the next day. The whole algorithm changes here, and so rather than going to the gas station once a week, every week or two, you go to your plug in your garage every night and plug in, and next morning you got a day's worth of electricity again, depending on how far you drive that day. For the plug-in hybrid, the total range is generally up to about 400 miles, and that's about 50 miles electric only. And then that's with an 18 kilowatt hour battery pack. And the remaining 350 you'd have to drive using gasoline. And this, again, mine as an example, it's a 8-gallon tank. It gives you 350 miles. So that gives you an idea of 350 miles divided by 8 gallons in terms of the miles per gallon. It's almost, in the neighborhood of 45 miles a gallon or so when it's in the hybrid mode. Pretty much all of the hybrid vehicles and plug-in hybrids and the electrics use lithium-based technology for their batteries. And again, charging times depend on charging level. So let's talk about EV charging. This is going to be kind of, we're going to spend a little time on this because, well, for example, I got a call this morning from a friend who had an EV charger installed, and they installed it incorrectly. So, that's most unfortunate. It's actually pretty hard to do it wrong. I'm not sure how hard they work to get it wrong or what. Need more information on that still. But anyway, lots of code requirements, and in National Electrical Code 625.2 recognizes certain vehicles as electric vehicles. Okay, so there's quite a few, and the whole thing is they have to be able to be drivable on the street. If you can't drive them on the street, then like electric golf carts and forklifts are not supposed to be driven along the road out in front of your house. Okay, so they're not included in the 625.2. All right, so there's first, and they have to use rechargeable batteries, so therefore this kind of battery is not satisfactory for an electric vehicle. Okay. Oops, here's a Q&A. What do we got? What's life expectancy of EVs, the batteries, compared to gasoline vehicles? That's a good question, Joe, because all I can go by in this is, first of all, life expectancy of a battery. What is that? Is that the life expectancy until it is only good for 80% of what it was at the beginning? Or is it the day when the battery crumbles into dust? And I'm not sure anybody's really tried to figure that out very well yet. But round figures, it depends again how you use them, whether you use them properly or not. But there's generally no reason why the batteries in an EV shouldn't last for at least 10 years. We've had ours for 5 now, and there seems to be no effect on the batteries. They still seem to be perfectly happy to give the same amount of daily travel as they did when we first bought the car. So, of course, there are a lot of other things. Yeah, exactly. If you charge them too fast, then they get too warm. So there's so many things that can impact the life of batteries. And as Rick points out, if you insist on charging them really, really fast, there's internal resistance in these batteries. And the square of the current times that internal resistance turns into heat. And that is generally not good for chemical reaction producing things. So, and that's impacted not by just charging rates either, Rick, because discharge rates can do the same thing. If you floor that thing and prove that your Tesla can outrun any Mustang in the whole world, if you do that a lot, you're discharging pretty fast as well. So if you want to get the most out of your car, you try not to charge it fast. We use a level 1 charger. I mean, we've got all night to charge the car. Why not use 10 hours to do that? Because that keeps the batteries relatively cool when we're charging them. And the only reason the higher charging rates are coming up is because they are in fact reducing by better design and construction of the battery packs themselves. They are reducing the internal resistance of the batteries. So if you get that resistance down far enough, then you reach a point where the heat generated during charging process is relatively negligible up to a certain amount. And that's kind of like the wind resistance on your car. It's relatively negligible until you get up to a certain speed, and then all of a sudden that wind holds you back and it's much harder to go faster, and it takes more. You have to step on the gas a little harder to. So again, the amount of force you require is dependent on how fast you want to drive and how fast you want to accelerate. So yeah, lots of things involved here as far as exactly what to expect. But we bought the guarantee because we weren't sure. So we have a 10-year warranty on our batteries, and it drops off a little bit after year 5. So that's the best they could do at the time, because there just weren't enough of them out there and not enough experience. We've now had a fair amount of experience with battery backups, photovoltaic systems, to know that a properly set up system with proper charging and discharge rates should easily be able to last for 10 years. I had some friends who had a set of batteries, lead acid batteries, last for their PV system. It lasted 14 years. So and that's lead acid. And had they been lithium, it probably would have been more. Okay, so moving on, let's look at some fuel costs. Everybody likes to talk about fuel costs. What do we have? Q&A here. Mindy, is it true there's electric vehicle battery shortage and it's a problem for companies that are stalled during production? You know what? I wish I knew the answer. I do not know. Does anybody know whether there's a short of EV batteries? What we know from the PV business is that people do tend to have to wait for certain kinds of batteries. We've had people waiting for a long time to get their Tesla batteries. And maybe that's because Tesla has been focusing on putting their batteries in their automobiles. It wouldn't surprise me that pretty soon there's going to be a battery shortage, just because the demand for EVs is going up and the ability to manufacture the batteries may not be going up as fast. And if anybody has a better answer, we want to hear it. Okay. But that's an excellent question. There seems to be a shortage of almost everything these days. If you've had any friends who've been in accidents lately, it seems like the favorite thing the insurance company likes to do is to total the car, because then it can be used for parts. So weird times, that's all I can say. It's so strange. Anyway, let's compare operating costs of a gasoline operating of electric vehicle versus gasoline, just to see. We're going to talk about pollution components as well here in a minute, but this is just dollars here. And if we got $4 gasoline, and it's been bouncing around there a little above and a little below, and let's say we have 15-cent electricity. Interesting thing about this 15-cent electricity, if you're on a general service demand rate, your cost per kilowatt hour, and in fact your nighttime cost per kilowatt hour, could be pretty low. I was just talking to a friend in California who said that if you buy nighttime electricity in California, you can buy it for 5 cents a kilowatt hour. And a few other places, apparently, if you get in a nighttime oh, that was not a friend in California. That was one of my grandson in Minnesota who said that if he installs the charger that is on a separate meter that only works at night, he can buy electricity for 5 cents a kilowatt hour. So that affects my analysis right here by a factor of 3. But again, everybody out there is an engineer and architect, and everybody learned how to do multiplication and division and subtraction and addition by the 4th grade at least. So just change the numbers to fit your particular situation. Love those full-size SUVs. You get about 20 miles per gallon. So 1,000 miles is going to cost you $200 for gas. Straightforward, just like that. Baby SUV at 30 miles per gallon, that's only $133.20 for 1,000 miles. All right, then if we have a hybrid at 55 miles a gallon, this little Hyundai loves to get 55 miles to the gallon. Well, then that's going to cost you $72.80 for your fuel. And if you got either an electric vehicle or a plug-in hybrid that operates electric only, at 15-cent electricity, that's going to cost you $37.50. Okay, so that's a pretty big difference between $200 and $37.50. And if we do half and half with the plug-in hybrid, cost goes up to $58.75. Okay, so now let's talk about charging levels a little bit. Level 1 uses 120 volt outlet, charges at somewhere in the neighborhood, somewhere up to 1,440 watts. And the reason for that is because then they can be used on a 15 amp circuit. And if they pull 16 amps, then that's the maximum continuous current allowed on a 15 amp circuit. And it's conceivable if you're charging for more than 3 hours, you might pop a circuit breaker. So that's level 1. And the charger looks like the one sitting up there on the right-hand side. Level 2 is it can use either 208 or 240 volts, single phase usually. And the charging rate is somewhere between 3,000 and 9,000, and it's up closer to 9,600 these days. But again, whatever number you've got, it's easy to figure out how much current that's going to be, so you can decide how big your electric service needs to be, or at least how big the circuit breakers, the wire, and whether or not their existing electrical service can handle it. Okay, so these are what typical charging rates, 208, 240 volts, whether you got a small level 2 or a larger level 2. You're typically using a 40 amp circuit, but sometimes a 50 amp will be used if you're using like a 9,600 watt charger. Okay. Level 3, that charges at 125,000 rate. And that's the one that really does a number on the batteries if you charge that fast. I mean, imagine look at 125,000 watts, you're looking at 347 amps, 3-phase. And I squared R on 3 different legs, whatever. And anyway, it's kind of what you have to do if you're driving long distances. You don't have much choice, but probably not the one that certainly I would avoid doing that if I had the option of charging with level 3. I don't have that option, so I don't worry about it. And the higher charge rates are on the horizon because, we're not just doing cars anymore. We're doing buses and trucks and stuff, and they can hold a whole lot bigger battery pack. How long does it take to charge? Well, usually an EV gets about 3 to 4 miles per kilowatt hour for a typical automobile. And again, it's how you drive it, all kinds of variable things, the same as getting 20 miles per gallon. Somebody can drive that car 25 miles per gallon. Somebody else will drive it and get 15 miles per gallon. So it pretty much depends on the driver, but things do tend to average out. So with this number, With a level 1 charger running at 1200 watts, you're going to get about 4.8 miles, or roughly 5 miles for every hour of charging. Okay, so you say that, okay, fine, we're charging at 5 miles an hour. And that doesn't mean the car has to be moving 5 miles an hour to charge. It means that for every hour that you have the charger connected, it adds another 5 miles to your battery. Okay, as far as how far you can drive. So for 50 miles, charge 10 hours overnight from 8 to 6. Why not? 9 to 7. There you get your 50 miles for the next day. Okay, level 2 charger at 6,000 watts. Okay, well, 6,000 is 5 times as big as 1,200. So that's going to give you about 6 kilowatt hours per hour. And so therefore, gives you about 24 miles, or close to 25 miles an hour for hour of charging. I've tried this. I've sat at the Palm Beach County Airport cell phone parking lot has a couple of EV chargers, level 2 chargers, and I've plugged in. I've driven up that airport. I plugged in and I looked at my electric battery tank, how many miles on it when I started, and a half hour later, and sure enough, there's about 12 more miles added to my battery. So the numbers fill out pretty well. 125 kW battery charger would add 125 kilowatt hours per hour, but even the big Teslas only hold 100 kilowatt hours. And with the big chargers, they only charge to 80 because they find that when you get up to 80, then you got to really back off. Otherwise, it's not so good for the batteries. So anyway, level 3s, they're out there, but obviously not in any kind of residential situation, not with that kind of power, not with that kind of a load. All right, so what kind of features would you like in your battery charger? Well, you have a basic charger. It'd be nice to have compatibility, communication, charging time. Not very expensive to install. Needs to be safe, needs to be code compliant. So here's one. And it's interesting to identify the pins there. You can see there's the 3 big ones. That gives you a line 1, line 2, and ground. And it's possible line 1 and line 2 will just be 120 volts to ground. Those 2 little ones are your control function and communication function. So they go back to the transformer part and the control part of the charger. And they, for example, if your car is plugged in, when you try to drive away, it won't go anywhere because those 2 little holes tell your car that don't you dare move until you unplug yourself from the charger. And so you get out and you unplug from the charger, and then the little light goes off and you can leave. So this proximity detection is interesting. You really don't want to drive when your vehicle is plugged in, and they're set up so that you can't do that. Now, if you have an advanced charger, you'd like it to be bidirectional. Why? Well, simply because think of having a 100 kilowatt hour battery pack. You're parked at work. You're not going to go home until 5 or 5:30. If you're an engineer, you're not going home until 7:30 or 8 probably. And the utility is talking to your car and it's saying, hey, at 4 o'clock, I need some electricity. I've got a peaking problem. I need you to, if you could, please supply 5,000 watts for an hour. And there sits the car with 100 kilowatt hours in its electric tank, having been sit there plugged in all day. And it says, are you kidding? Is that all you want? I'm happy to sell that to you. It all depends on the price. And so the utility and the car, they negotiate automatically, of course, and within another about 100 milliseconds or so, they've settled on a price and the car is sending electricity to the grid. So this is going to be really exciting. And there's some experiments going on right now. The For example, the Tesla batteries that you use for a solar system are bidirectional. All it takes is one extra inverter to be able to return AC back to the grid. So adaptable and portable and smart. Those will be the features of the chargers of the future. Okay, another question. Let's look at it. While an all-electric US vehicle fleet seems very attractive for many reasons, it's important to note that proliferation of electric vehicles replace fossil worldwide mining. Yeah, okay, sure, right. Yeah, there's some an article just yesterday about how they found a substitute for some of the rare earth elements for electric motors. In fact, they discovered it in extraterrestrial asteroids that have, or what do you call them? Those things, meteorites, that they've analyzed them, and there's a special iron nickel compound in there that they can now fabricate with iron and nickel to create the kind of magnets that don't need fancy rare earths to do. So my response here is, yeah, so why don't we all just continue building gasoline vehicles, because they'll be fine. Nothing is perfect, and we may have to take another look here, but I look to the intelligence of the engineers and the research scientists out there to come up with better solutions. Because sure, nobody wants to chop the top off a mountain, but if we're going to continue our driving habits, if we're going to continue as we go, we have the option of staying with the fossil fuel. And of course, there's no such thing as global warming or anything like that. But there are a lot of stories going around, and they all should be listened to. But I have to believe that technology is advancing a lot faster than we imagined it would, and we're going to have to look to see what happens. Okay. I mean, after all, we are making all kinds of things. Concrete, for example, is incredibly energy intensive. And we're going to have to take a really hard look at everything we do. And it's all going to boil down to the money it costs, because energy is money. And if there's a lot of energy involved in it, there's a lot of money, and the cost of it goes up. So that's ultimately, in my opinion, going to be the driving factor here. But good point. I appreciate you bringing it up, because it's that piece of information is going around a lot. I see some chats, but if we're doing a conversation here, we need to move the chat to Q&A unless the chat is an administrative issue. Okay, so let's see. Oh, I didn't click the done. Okay. So moving on, what's a typical charger look like? Well, this is that simple level 1 charger. And you can see it has a standard 3-prong plug to plug into a 120-volt outlet. And there's a few little holes in the thing. You can you can screw that up to your wall. You want to keep it 18 inches above the floor if you're in a garage. You need to do that for any kind of an electrical outlet. And otherwise, the rules are pretty straightforward on that. This is level 2 charger. This is out in front of the Nissan dealer, believe it or not. And here's level 2 that you might mount in your garage. And here's level 2 that you just might find out in front of the local library. And here's level 2 that you just might find out in front of the local university. So there's lots of, and they look so nice. Don't they look nice? And the nice thing is, once you plug it in to your car, you don't have to go wash the gasoline off your hands. So there's something attractive about that too. I might be sounding like I'm kind of anti-fossil fuels, but that would probably only be because I sort of am, because I Unfortunately, I think I understand what they're doing to us. And I think we need to rethink the whole thing. But anyway, this is not to be a political discussion. It's an economic and engineering and technical discussion. So on we move. And so what are some of the code standards and abbreviations? Question, let's see what we got. Heavier battery in EVs results in having to change out your tires every 20,000 miles or so. I don't know if there's any validity to this, but we've driven around 25,000 miles now, and our tires look just every bit as good as they did when we first bought the car. And so I think this is maybe another one of those interesting but not so true observations. One thing we've not had to do, or at least the people with the electric cars, they don't have to change their oil very often. And there's a whole lot of other things they don't have to do. So I don't think this is right, Patty. I can't prove it, but intuitively and based on my own vehicle, it doesn't compute. Okay, NEC 625. It talks about the different kind of connectors, okay? And this is the big one here. It's the SAE J1772. That's one you've been seeing picture of all over, and that's pretty well standardized now. And that same plug-in will work on either 240, 208, or 120 volts. The plug-in itself plugging into the car, the front end where the plug is, and the isolation transformer and so forth, that has to be set up for the particular that has to be set for the charging current. This OCPP is interesting, Open Charge Point Protocol, and that enables communication among different chargers, so that you could have like 10 chargers all working together, except you may have a limited demand. You may want to do demand limiting. And so these chargers can talk to each other and share and say, okay, either we all back off and do 5,000 watts instead of 9,000 watts, or half of us do 9,600 watts while the rest of us shut down. In any case, they get to have a little conversation about how they want to make sure that everybody who's plugging in is happy, even though they have to diversify the load because there's a lot of vehicles being plugged in, and they don't want to have this 9,600 watts for every single vehicle 100% of the time. All right, the UL standard 2202. You can buy it for $1,000 if you want to go into the business of manufacturing EV charging systems. Oops, more questions. Let's see, Tesla weighs significantly more than a similar size gas plug-in, and it does go through tires more quickly. Okay. My guess, though, is your total maintenance cost is probably less, or probably not more. Because there are a lot of things you don't have to do maintenance on with your Tesla that you do have to with the gasoline engine. So I'd love to see an article where somebody does the total maintenance scenario for gasoline cars versus electric cars. I think that'd be very useful to have that available. And just intuitively, based on the additional maintenance we've had to have on our vehicle in the last 5 years, it's almost nothing. So, I mean, we take it in once a year because we paid for the privilege to do that. But we simply haven't had any issues with anything. So even if we have to buy, our tires wear out 20% faster or something like that, I think it's going to be made up by other things not having to be dealt with. Europeans adopt the same standards. I think They may very well have, because, and again, this is, I think, I don't have the answer. Is there anyone else who is familiar with European standards, how they compare with the United States standards? I kind of figured most of us here are in the United States and we're concerned with the US, so I didn't look up the European standards. I don't know, Joe, I'm just not sure. But Paul points out that, yeah, it is still a whole lot less costly to operate and maintain his Tesla, even though he may have to change the tires more often. Well, you already saw what the comparative cost of gas and electricity is. You can buy a lot of tires with that. I blew a tire on my daughter's car a month or so ago, and it ran over something really nasty and it had to be replaced. Of course, you don't replace one tire, replace two of them. That's $450 for two decent car tires. But you know, how much gas and so on. Anyway, yeah, I think we probably are all set here. Okay. Yeah, I really appreciate all of the questions. It makes it a whole lot more fun for me. I just get some concern. I'm going to look at my clock here and see how we're doing. It's 3:07. So we've got more or less another hour, but not quite. I might have to start clicking. What I'm going to do is I'm not going to read all this stuff anymore, because everybody on this program can read. And when I click a page here, you can see what there is available, so that if you're really interested, you simply download the slides and then you can read these at your leisure. All right. So I'd rather have the discussions than read stuff to you that you can read yourself. All right. I just want you to know there's a lot of stuff out there. And there's Green Car Reports is a good reference for what's EVSE and so forth. And here's another Wikipedia, Open Charge Point Protocol. Okay. So let's say that we decide we're going to put in a charger. And that would be probably we're going to put in a level 2 charger, because if you buy an EV, I don't know about the Teslas. Do they give you a level 1 charger with the Tesla, or does it come with it in the trunk? Ours came with a level 1 charger, and I decided to use it. Let's see, I think this is the answer to the Tesla. Now, yes, they give you a level 1 charger. Okay. So the idea is try it out and see if that level 1 charger is all you need. And if that's all you need, which in fact is what our case is, we didn't have to invest anything further for adding our charger. It came with the car, and I can unscrew it from the wall, throw it in the trunk if I want to go someplace else, and then plug it in that other place. We in fact did that while we moved out for 3 months during some remodeling going on last week here. So question here for an invoice from a Florida car dealership for a hybrid battery replacement. Invoice totals $26,853.99 for the battery itself. Maybe so. So that would be in 10 years, that would be almost $3,000 a year for the battery, wouldn't it? So need to include that in the ownership cost. And again, this is thank you for that information, because if it really does cost that much, we add that, because the whole thing we're looking for is a life cycle cost here, and we need that information. So this is good information. Now, is this a hybrid battery replacement? Is this for a hybrid vehicle? This sounds pretty unreasonable for just a plain old hybrid. I mean, you can buy a hybrid car for less than that. So this does not sound reasonable. Somebody's trying to rip somebody off. We're seeing a lot of rip-offs these days in terms of used cars and other things. So this could be supply chain stuff, but this is not a realistic price. Maybe it's what you're getting, but it is a rip-off, that's for sure. All right, if you're going to add a charger, 220.83 gives you the, well, Article 220 tells you how to calculate the service size for a single family dwelling. And if you have an existing multifamily dwelling, 220.84 tells you how to run that calculation. And there are other sites of the National Electrical Code for like a commercial or whatever. But let's do the 220.83 example. Let's say we got a 1,500 square foot dwelling, no new air conditioning, no new heat, just we're going to add a new charger to it, okay? So let's do the calc. Yeah, let's say that it's about a 3-ton air conditioner, and that's about 3,600 volt amps. General lighting, 3 volt amps per square foot. Any of double E's have done this calculation over and over and over again. For the non-double E's, this is all coming straight out of the rule book, the National Electrical Code. And again, this is the number you get. You have all these things, the 5.5 kW level 2 charger we want to add, that plus the electric range plus the electric water heater adds up to 22,000 volt amperes. The washer, dryer, refrigerator, and 5 appliance circuits. Normally you'd list them individually, but then that gets, my screen isn't tall enough for that. So I kind of have to do it this way. So you take your first 8 kVA, not the first 10, but the first 8, because this is an addition, not a new, but we're going to add something. So the rules, you take the first 8,000 volt amps at 100%, that's 8,000. And the and instead of the first 10,000, and because you've already included your air conditioning and so forth, and the remainder comes in at 40% or 15,240. So what does that mean? Well, it means that you need a 96.8 amp electrical service to handle all that. Well, the National Electrical Code says minimum electrical service has to be 100 amps. So that means you can add a level 2 charger at 5.5 kW level to almost anything. But you should always do the load calculation first to make sure you're okay. You may have to upgrade the service. If so, maybe so. But remember, it's really only adding in 40% because of the diversification factor. All right. So the other thing, of course, is you need a room for a 2-pole 30 amp circuit breaker in your distribution panel. Otherwise, you may need to do something else, like a line side tap at the service entrance or something, but or maybe even replace the main. Who knows? There's so many options that you discuss that with your local. Well, you guys are engineers and architects, so you decide what you want to do yourself, of course. Forget about discussing it with somebody else. You've got the numbers, you got the calculator. Okay, the alternate surface calculation. Here's a question. Let's get it right away. LED lights. Oh yeah, well, no, the thing is, this general lighting requirement of 3 watts per square foot has been around forever. And the National Electrical Code has simply never changed it. And that's why the calculation is so conservative. It's incredibly conservative. Even the air conditioning and everything else, refrigerators, 1,500 watts for a refrigerator. Try plugging your refrigerator into one of those kilowatt meters once and figure it out. Your refrigerator is probably not using more than 300 watts. They used to be pretty high because they used to have an electric heating element around the door to prevent condensation. Now they just insulate them better. So, but yeah, Rick, you're absolutely right. This 3 watts per square foot is a lot. And almost never are you going to be using that much. And others have done things like, well, here's how you can find out with the alternate. If you don't think you're using 3 watts per square foot, you can use this alternate calculation here. All right. And when you do that, all you have to do is measure for a month or for 12 months. If you look at your peak demand over a 12-month period, of course, who's going to connect a meter for 12 months? But then it says, well, all right, but you don't generally have a demand meter in a residence, for one thing. So it's okay to measure the demand for a month. That is, put an ammeter on a recording ammeter on both of the two hotlines coming in and measure the current that's coming. And then find out which one peaked out at the maximum value over that month. And you can use that then as your load. Actually, you have to add 125% of that. But then you compare your measurement with your calculation from 220.83, and maybe you don't have to upgrade your service after all. So you try them both. If you come in, if 220.83 works, then you don't mess with 220.87. But if 220.83 does not work, then you may want to try 220.87 before you go to the expense of changing your main distribution panel out, or your main service out. Okay. For the previous example, if your result came in less than 23.24 kilovolt amperes, then you can use a smaller one. Okay, so where are you going to connect it? Well, if it's convenient and if there's space for a circuit breaker, you can use your main panel. But if you can't, then there's other ways to do it. And there are provisions in the National Electrical Code for tapping your feeders between your main disconnect and your distribution panel. And if you know the size of the charger, you can determine exactly how big the overcurrent protection needs to be. And 125% of the load gives you the branch circuit wiring. So that's straightforward, no big deal there. Compare your charger conductor ampacity with the main circuit overcurrent protection. And then you follow 240.21b2. And it all depends on whether you're doing a 25-foot tap or whether you're using a 10-foot tap. But that tells you how big your wires have to be. All right. And if you have a larger main breaker, then you're probably going to have to reduce the distance to the overcurrent protection to 10 feet, because otherwise you're going to have to use too big of a wire, maybe a whole lot bigger than you would normally need for that size circuit to charge your car. So here's a little picture. This just happens to be a condominium electric power room. And each one of these meters feeds into that trough above, which then ultimately goes to the unit in one of those floors above, any of those 12 floors above that. So why not put a disconnect here within 10 feet of that meter, and then run those wires into that trough? You can see where the screws are. You just take the cover off and find which wires come from the meter for the place that you want to charge the electricity to. And you feed from there, and there's your custom meter over here, customer meter and main disconnect right under it. And out there on the other side of that wall, there's the garage. So you may have to go 50 or 100 feet along the garage wall, making careful that you don't have a ceiling that has post-tension cables in it, because you don't want to mess with drilling into a ceiling with post-tension cables unless you got a mighty fine X-ray machine or ultrasound machine to find where those cables are. And unless you're willing to pay somebody who will certify that they are in the right place, maybe you're able to certify them yourself. If so, that's fine, but that's the issue. Anyway, this is great for a tap at the main overcurrent protection, to put in a disconnect here so that you can have 40 amps worth of charging out at your vehicle. Here's some more stuff from 625. And again, all stuff that can be read. Some more, lots of stuff there. Okay. Now here's one that's really interesting, 625.48. That's the one I've been talking all around, the interactive systems. And that goes back to 702 and 705. 702 or 705 refers to, that's the part of the National Electrical Code that the solar guys use all the time, because 705 is the connection of a compliant source, that is something that makes good sine waves, into feedback to the utility. And it tells you all the different ways you're allowed to do that. And basically it says if you have a UL 1741 compliant sinusoidal AC source, then you can use one of our provisions in order to tie into the utility. So this one's going to be a hot one here in the next 5 years. Watch it carefully, see what happens. Make sure the charger is more than 18 inches above the floor. This is the thing about if you have a gasoline car in there or whatever else, and you get that gasoline smell in the garage and you get this flammable gas, but it's heavy and it usually stays lower than 18 inches above the floor. So more stuff. So here's what we're looking at, the difference between the two chargers, between the bidirectional and the single direction. Okay, I want to be able to move past this. It's 3:22 though, so let's move past the electric vehicles and let's talk a little bit about energy efficiency, okay? Because there's lots of different energy efficiency things that can be done, and a lot of them that are very cost effective and need to and ought to be done. And again, if you save, it's a payback thing. How long is it going to take for your investment to pay back? Or how long is it going to take, addition of the additional insulation, how much is that going to increase your mortgage payment versus how much is that going to decrease your electric bill or your heating bill with whatever other means you might decide to heat? But almost every building out there can be made greener one way or another. They even made the Empire State Building greener. Okay. If they're heating space, food, or water with fossil fuels, a lot of times you can put renewable electricity equipment in. Refrigeration, air conditioning, ventilation can be made a whole lot more efficient. Here's your LED lights, better doors and windows, plugging up air leaks. We were grateful for that last night. We waited for the hurricane to come by. It hit about 50 miles north of us, but fortunately we had hurricane glass on all the windows and there were no air leaks. And that's helped us on our air conditioning bill by, it's interesting what you do to, sometimes it has more than one effect and sometimes they're all good. But just so many different things, landscaping, and in fact, not just watering your lawn. There are so many smart lawn watering things out there. We'll take into account how hot it is outside, what season it is, whether your lawn needs more or less light, water. They even take into account whether that particular part of the lawn is shaded, and then it doesn't need as much water. So it's very interesting stuff out there. And furthermore, you check it out on your phone if you're far away and see if it's working the way you want it to. So there's so many cost-effective retrofits out there, and all of them for the asking. Look at this neat system here. Once upon a time, I remember discouraging heat pumps because below 40 degrees Fahrenheit, they had to have auxiliary heat outside. Now these things run down to minus 13 degrees Fahrenheit, this particular heat pump system. A ductless system, mini split, and has a seasonal energy efficiency ratio up to 33.1. That's an incredible system to install. At least twice as high as most of the SCERs that are out there right now. Here's some more stuff, an energy recovery ventilation. This is a very simple countercurrent heat exchanger that brings in outside air and vents out inside air. And if the outside air is cold and the inside air is warm, the inside air leaving warms the cold air coming in, so it's warmer, and vice versa. Now, if we need humidity control, and you have an energy recovery ventilation, this thing actually, if it brings the incoming air down below the dew point, you're going to need a condensate drain for this thing because it actually dries the incoming air a little bit as well. The efficiency of these things is incredible. It says up as around 90%. So consider that instead of the regular way of getting fresh air by infiltration or whatever. If it's cold outside or really hot and humid outside, one of these can really be nice. And if you don't have a humidity problem, you can just use a heat recovery ventilator. And I'd be kind of curious how many people actually have either an ERV or an HRV. Let's do this one a little different. I'm going to take a look at my participant box and just raise your hand if you have heard of any of these three systems. If you have one or if you've heard of one. I guess let's just, if you have one first, how about those who have them? Oh, that was quick. Okay, and how many have heard of any or all of these? All right, pretty much everybody's heard about them. So we got a bunch of pretty astute engineers and architects out there. All right, thanks, appreciate that feedback. Because there's some really neat stuff out there. And that's just a few. Domestic water heating. Used to be the only way to go was solar water heating here in Florida. But then you start thinking about it, the cost of a solar water heater. And then you think about electricity made with PV that's worth about, say, 6 or 7 cents a kilowatt hour. And then you install a water heating heat pump or heat pump water heater, whatever you like, because they, in fact, extract heat from the local surrounding air and dump it into the water. It's a heat pump, all right? And they have a coefficient of performance around 3.5. So therefore, 1 kilowatt hour of electricity used, it produces about 3.5 kilowatt hours of heating. And of course, you can convert that to BTUs and so forth. Every 1 BTU is 3,413. I'm sorry, 1 kilowatt hour is 3,413 BTUs. Everybody knows that, I think. So interesting to do the numbers on these things. So therefore, if you power a heat pump water heater with solar or even with utility, it might be less expensive to heat your water than to invest in a solar water heater. And my solar water heating friends may not like to hear that, but I mean, I had one of the first solar, my family, had put a solar water heater on our roof in 1975. So it's not that I'm against solar water heaters, it's the prices have gone up. And if you're a seasonal resident, you can't use that hot water when you're not here. So then all of a sudden, the amount of hot water you make that you're pricing out against the cost of the water heater, probably you're going to be better off with photovoltaics and a heat pump water heater, because then you turn the heat pump water heater off when you leave and the PV makes electricity and you get paid for it, and let it run your air conditioning, your refrigerator, whatever. But otherwise, you get paid for the electricity you sell back to utility. Here's a Q&A. Heat pump water heaters also dehumidify the air used to source the heat pump. Yes, exactly. Okay. And they cool it. They cool it and they dehumidify it. And so if you're living in Florida and your water heater's out in your garage, it gives you a little additional air conditioning out there. It's not like putting a 3-ton air conditioner in your garage by any means, because your heat pump water heater only runs when it has to heat water. And if you got a tank full of hot water and you don't need to shower or dishwasher or laundry for a while, it's going to be shut off. But folks I know who have them in their garage are quite pleased that they give them a little bit of relief from the humidity. So yeah, Stan, maybe you have one. Stan, do you have one? You want to type in a quick response to that while I still got my let's hear. Yeah. So you'd recommend these then? You think they're pretty good investment? You think you're getting your money for the marginal cost. Marginal cost on this is probably about $700 for a 50-gallon unit. Is that about what you paid, do you figure? Yeah, so that extra $700 marginal cost is going to pay back in a few years. So the payback is incredibly good with these machines. Furthermore, they tend to have a longer guarantee, a longer warranty than a conventional water heater, which is interesting. Because one of the things that I think they do is they put a little bit bigger sacrificial anode in them so that they don't die quite so quickly. So that's another added benefit, that they have a longer warranty. You don't have to replace them quite as often. So yeah, that's and this is just a few of the really neat things that are out there. And you know, they're there for the purchasing and installing and specifying and so forth. There's your cool your surrounding space in Florida. May or may not want to do that in New York in the wintertime, but the amount of cooling is generally not so much that it's going to be offensive. And here's one of them. This one's an A.O. Smith model. Just look in your Home Depot catalog or whatever and see what kind of water heating heat pumps they've got and what they charge for them. But I noticed, so we were very seriously thinking about one for our condo, but our water heater is in a relatively cramped closet, and I had some concern about that cold air around it condensing. And if that cold air condensed on the wall, that would not be a happy thought, because mildew is a major problem as well. So finally decided just to get a smart water heater rather than and the smart one's the one that if it senses it's got a puddle of water underneath it, it shuts off the water supply to the water heater. Have to do something smart, right? Here's a smart irrigation I was telling you about. Again, I'm going to type this and just hit my advanced button, because you can look at this again later. And here's the question. Put a heat pump water heater in my aunt's basement, replaced an oil-fired indirect storage tank, ordering less oil, and got rid of the dehumidifier in her basement. Fantastic. All right, so Edward, that's great. Thank you for sharing that. That's fantastic. I knew they were good. I wish I lived in single family. That'd be the first thing I'd do to modify, other than, I mean, that'd be the next thing I did after I put a PV system on, if I didn't have one already. What else we got? Oh, I forgot to hit the done button. Okay. Let's talk a little bit about zero energy building. Let me look at my time here. 3:33. Okay, good. We got a half hour. What is a zero energy building? It is not a building that doesn't use any energy by any means. That would be a little crazy. I mean, a tent, I think, is called a zero energy building. But who knows? If you define a site boundary, and if you put in that site either a building or a couple of buildings, a campus or whatever, and if you have within that site boundary the production of renewable energy, and oh, I left an arrow there. Oh well. And if you buy some energy from the utility, and maybe some energy from whether it's natural gas or whatever other fuel source it might be, and if you then export some renewable energy to the rest of the world, such that the green one and the pink one match up, that the amount you export equals the amount you buy, then you are a net zero energy unit. All right, it doesn't make any difference whether you're a school. I just learned that we have one of those up not far from where one of our participants is living. I don't know, Mindy, did you know about the zero energy school in Kissimmee? If so, I want to talk to you more about it one day. In any case, here's your definition, but now it's a little trickier than this, and let's see why that is. These buildings here, they should have had their service equipment a little bit higher up on the wall. And I hope we didn't get anything like this again up in Central Florida right now as we speak. That nasty storm is probably passing through near the Orlando Daytona area. Let's see, you built one. Oh, okay. 5-year payback. Good question. Good answer. I love the answers like that. Okay, thank you, Paul. what is direct building energy use? Well, it's simply, well, here's some numbers first. The kilowatt hour is 3,413 BTUs. So I didn't have that memorized, just I knew it was here. A therm is 100,000 BTUs. A barrel of oil is 42 gallons of oil, and it contains 5,800 or 5,800,000 BTUs of heat energy, not all of which can be used. Okay, as you know, if you put your hand on the hood of your car after you've been for a drive with your gasoline vehicle, and it's warm because it gives off excess heat. That did not help to move the vehicle. That's another interesting thing about Tesla owners. They put their hand on you know, there used to be this, you knew which car had recently arrived because you put your hand on the hood, and if it was hot, then you know it just got there. But it's a little tricky with the Tesla because they don't get hot. And so you don't know whether they just got there or if they've been there all day. Anyway, this is the BTU counts for these various energy sources. Now, given this, now we need to convert over and first make a list of all the energy sources that we expect to use and how much of them we expect to use, okay? So let's say, for example, you might want to rebuild this place and turn it into a zero energy building. And let's assume it's going to be one that uses 75 100 kilowatt hours of electric and 500 therms of purchased natural gas in a year. And so how do we make it a zero energy unit? Well, we first have to convert the electricity to BTUs. And 7,500 kilowatt hours times 3,413, that's 25 million some odd BTUs. And then we convert the electric BTU to source energy by multiplying it by 3.15. Why do we do that? Well, simply because it takes about 3.15 units of fossil energy to get 1 unit of electric energy. So we go to the source energy. All right, and this is something that's agreed upon by the folks who've done the analysis for zero energy homes and qualifying for that. So that means that the electric BTU source energy is 80 million some odd BTUs. Natural gas converted source energy, you only multiply that 500 therms by 1.09 because the natural gas is probably in a furnace or a water heater where you want that heat. It's just being used for heat, maybe your electric range. And so there's only about a 9% loss there. So you need 100, or you need 54 million. Add them all up, 135 million BTUs of source energy per year. So how do you offset it? Let's say we're going to offset it with photovoltaic, all right? Then we have to figure out how much PV do we need to create this many BTUs of source energy a year. Okay, so let's do the math. Let's use this 1,500, this magic 1,500 kilowatt hours per kilowatt per year. Okay, you can always do a simulation. If the number is different for your proposed system, then you use that different number. Okay, but 1,500 is a reasonably number to use as an example. So if we convert that to BTUs per kilowatt hour per year, that gives us 5,119,000 or so BTUs per year per kilowatt of photovoltaics installed. Okay, but now we have to convert it to source energy. Now this is interesting because this was made by solar cells. There's no heat loss type thing here. But we got to compare apples to apples. So if we're comparing this to utility electricity, it's every bit as good. The electrons don't know the difference. Generally, it's even better because the solar inverters are typically better sine waves than what you get from the utility. So anyway, so it's only fair to multiply these by 3.15, which means every 1,000 watts of solar that you add is going to give you 16 million BTUs per year per that 1,000 watts, all right, to contribute to your needs. So here we've got 135 million, and we're going to replace it all by solar. And we divide it by that 16 million, and it means we need 8.38 kilowatts of electricity for this, what was it, 1,500 square foot dwelling, something like that. So the question is, oh my goodness, the 8.38 kW, how much is that? Will it fit on the roof of the house even? Do we need a bigger backyard? Where are we going to put it? So let's do a little analysis here. After all, we love to do the math. Let's assume we have an array with 20% efficiency. That's very common these days. Compared to 10 years ago, the efficiency, or 12 years ago, efficiency of 13% was generally figured good. What does that mean? That means you can make 50% more electricity now with the same roof that you could have used 10 years ago. So not 7% more, 50% more, all right? Because 20 divided by 13, that's a big, big improvement. And it means you can make a lot more. Okay, so anyway, that means that 20% efficiency, it'll produce about 200 watts per square meter at 20% efficiency, with 1,000 watts per square meter as being the incident sunlight. So this 8,380 watts divided by 200 watts per square meter means you need 451 square feet of south-facing roof space to make those kilowatt hours that you need to offset the purchased electricity. All right. And so then you just price it out. And we already figured that out. We got the levelized cost of energy for photovoltaics. And if you're using 300 watt modules, this would be about 28 modules on the roof. And 451 square feet, well, you know, how about 15 by 30? Gee, that's not too big of a section of roof, is it? In fact, as it turns out, almost every residential house out there has enough roof space to make enough electricity to meet its annual needs if it is operated sufficiently efficiently. Try that one fast. Over the year. Okay. So you check the module dimensions, make sure they fit on the roof, make sure it won't blow away, and so on and so forth. But now, if you don't want to put as much PV on, well, maybe you can use one of these fancy water heaters, and then you don't need as much electricity. Maybe you can use one of these fancy heat exchangers and not need as much electricity. Maybe you can upgrade the efficiency of your air conditioner and not need as much solar electricity. So you do the math and decide what's more expensive, the solar or a better refrigerator or a better air conditioner. And do it on a life cycle basis, so not on an annual basis. And make sure you take maintenance and all that stuff into account. Let's look at this question. Oh, well, of course, orientation matters. Yeah. And when we do our solar, but let's be a little more specific on orientation matters. Depending on the location, typically either an east or a west facing array will lose about 15% over a south facing at a good tilt. All right, if you're facing north, and by golly, I had a system this morning, it came across my desk, it had some north facing array, and that north facing array was making around 1,000 to 1,050 kilowatt hours per kilowatt per year. So yeah, you're going to lose about 30% if you look north. So that increases your cost per kilowatt hour from maybe 6 cents to 8 cents. But gee whiz, that's still cheaper than what you're paying for the utility. So it's amazing how many systems we are now seeing that are putting modules on east, west, and north roofs, and they're putting them everywhere they can find a place to put a module, because when you do the math for the total performance of the system, it still looks really good in terms of payback and everything else. So yeah, thanks for pointing out the orientation thing, because but again, simulations are available for simulating almost everything. And Paul, I'm going to give you, in case you're interested in generating some of your own numbers, and everybody else, the National Renewable Energy Laboratories out in Golden, Colorado, has a really nice program. It is available for free to anybody who wants it. It's called the System Advisory Model, SAM. So just Google the National Renewable Energy Labs and tell it you want SAM, and it will ask you for your email and a few questions, because they got to prove that you somebody is using their product, because after all, it's produced by the government. But you get this lovely simulation, very intuitive tool you can figure out how to use in 15 minutes or less. And PV Watts is one of the options in the, PV Watts is straightforward because it's not system dependent. It doesn't care what kind of module or inverter. But with the SAM, you can actually choose the inverter and the modules that you want to use in the system, and it takes into account the efficiencies of these particular piece of equipment. So if you've used PV Watts and liked it, you're going to love SAM. Let's put it that way. So give it a shot. I'm sure you're going to love it. Okay, let's see here. So trade-offs, of course there are trade-offs. And that's why we're engineers and architects, because we're used to doing trade-offs. Do we put in the waterfall or do we put in the whatever else? So in any case, greater efficiency usually compared to the cost of more or less renewably generated electricity. And I use the word PV, but if you're in a place where you can get low head hydro, or where you can get a geothermal or wind or any other kind, you still compare the cost of it. And that's going to be generally your deciding factor. I mean, some people say, oh, I'm just doing this because it's the right thing to do. Well, there are some crazy people in the world who do things like that, but most people care about the money. And so they just want to make sure they come out at a good deal. I mean, I have never seen anybody price out the cost effectiveness or life cycle cost of a statue of a lion out in front of their house. On the other hand, they really want to do the life cycle costs on a photovoltaic system on the roof. Again, that's for the psychologist to figure out. I'm just a poor old engineer, and I never have claimed to be able to figure out people. Anyway, yeah, as you pointed out, Paul, the orientation makes a difference. And in fact, I actually have a slide that shows that. All right, so let's take a look at, well, here, this slide here. We're going to look at this one first. This is the, if you build a zero energy building, it shows the monthly energy savings cost versus the additional mortgage cost. In other words, you have to spend an extra $19,548 to get to zero energy in Atlanta, but it's going to save you $152 a month on your energy bill, and it's going to cost you an extra $100 on your mortgage, so you're $52 a month to the good by doing that. If you're in San Francisco, even better. Electricity is a little more expensive up there, and you're looking at $217 in savings versus an extra $91 on your mortgage. Now, other things happen as well. There's a thing called insurance and whatever, and then oftentimes the building a better structure will get you better insurance rates. So there are other peripheral effects as well. Let's talk a little about energy storage, because there's a lot that's going on with energy storage. Small ones been around for a long time, especially with photovoltaic systems. Standalones pretty much have to have batteries. They don't have to if they just work during the day. There are DC coupled grid connected systems. There are AC coupled grid connected systems that have energy storage. Okay. And historically, they've been fairly costly. And even today, they're fairly costly. But you don't look at these as a payback normally, but you look at these systems as an insurance policy. It is so nice to have your freezer working so that you don't have to empty it and figure out what are you going to do with all that good, expensive seafood or whatever you've got stored in there. If you know that you've got battery backup. So anyway, there's a lot of been going on, and some of the systems have been kind of expensive and complicated, and a lot of on-site programming. And sometimes after the person who installs it gets on programming it, then the owner gets out there and says, I'm going to change this. And then all of a sudden the batteries die in 5 years instead of 15 years because they've set the charge limits wrong, whatever. So normally what people got was the utility meter and a main disconnect in a main distribution panel. That's been historically kind of what's going on as far as storage is concerned, because it's just been a little complicated. I mean, we started the company that I used to work for as sort of a hobby. We started installing battery backup PV systems in 2006 after our area had been zapped by 2 hurricanes in those 2 years. People were getting tired of standing in line waiting for gas. But guess what happened? Now, thanks to Mr. Musk and the Tesla battery, and a whole bunch of other vendors now who are doing similar things, by the way, but everybody knows about Elon Musk and the Tesla battery. You've got your meter, you got your main disconnect, you got interruptible loads maybe in that main disconnect. And then you got this disconnect relay thing that we'll talk about in a minute. And then we put the main distribution panel with the main circuit breaker in it here, and we call these the uninterruptible loads. Now, how can they be uninterruptible unless there's something to replace utility when utility goes down? So we better add something, thing called a combiner panel. And that must be there because it's going to combine some stuff. So maybe we should have a little solar to go in there. And then maybe we should have some kind of a battery, like a power wall. And so now, when utility goes down, that automatic relay opens up and you've got a standalone solar system with battery backup that keeps your refrigerator running. And it's pretty straightforward. Not that hard to install, not that hard to design, and still not particularly cheap. But the typical single Powerwall battery is about 13.5 kilowatt hours of storage. I think the biggest system we've designed is maybe use 4 of those. So that's about 54 kilowatt hours, roughly the amount of storage you'd have in a electric vehicle. Anyway, here's a basic layout of a modern battery backup system that is run on solar. And of course, this thing, when the utility is there, that automatic relay stays closed, and any electricity that you don't use with your main distribution panel then gets to be used by the interruptible loads. And if they don't use it, then it gets sold back to the utility. So nothing wasted here. It all gets put to use. So if you got the utility in the sun, that means you're just going to fully charge your Powerwall, and it'll power whatever you need to power. But sometimes if this utility is there and there's no sun, that means only utility power is available to all the loads if the utility is there. But if the utility goes down, then there's no power to the interruptible loads, but there is power to the uninterruptible loads, and that comes from the batteries and or the solar array. And the only thing is, you got to be careful, is if it's nighttime and if your batteries are running low, you've got no way to charge them up that the utility is gone, and there has to be some control in there to make sure that when the sun comes up the next morning, that storage system can tell the PV array that it's okay for it to turn on because it has use for the electricity, because the utility is not there to give the message to the PV that it's okay to turn on. So in other words, when utility goes down without battery backup, the PV array has to go down so that it doesn't interfere with utility maintenance operation. Here's a question. What do we got? Briggs & Stratton makes home energy soon and snow. Isn't that interesting? Briggs & Stratton, a generator manufacturer, and they're not the only generator manufacturer. The generator manufacturers are taking advantage of the situation, and they use their generator as the ultimate backup. If the PV battery runs out, then you burn some gas. But so yeah, thanks. I didn't realize Briggs & Stratton was in the business as well. What's that other big, I'm forgetting, that other large generation, Generac, yeah. Yeah, they've got a really nice DC coupled battery backup system, then they can incorporate their generator in with that. So yeah, there's some neat stuff out there. So let's move on here, though. We don't want to run out. Sizing the PV. All right, I'm going to go through this quickly because we are running short on time now. 4 minutes, 7 actually. So if you're really interested in doing this, here's how you do it. Okay, and you'll have to read this on your slides, and there are other good references out there, like in terms of the manufacturer's data sheets and manufacturer's installation manuals. And there are even some textbooks out there that you can read if you are really interested. There's in fact, the guy who's presenting this webinar, if you look up his name, Google it, you'll find a PV textbook by him that if you feel like you want to invest $100 or whatever they're charging. And then there's the large energy storage systems. Here's your pumped hydro. Anybody want to guess what this is? If you think you know what this is, please just turn on your mic and shout it out. What is this? Come on, mechanical engineers, it's your baby. What is it? Maybe this. Edward says turbine. It's kind of like a turbine. You know what this is? It's a flywheel. Believe it or not, it's a super high-speed flywheel. And this thing gets cranked up and it's going like crazy. And if the utility goes down, what these flywheels are really good for is frequency stabilization, short term. But this is a 1 megawatt flywheel. So do your half I omega squared on that and see what you have to have in order to get a megawatt of energy storage with a flywheel. And these things are coming out and they are cost effective, or they wouldn't sell. This is a commercial flywheel, believe it or not. So I felt that very compelling need to make the mechanical engineers happy that there's a very nice mechanical means. Of course, you have to turn it into electricity. And if you turn it into electricity, you can let the speed of this thing run down. If you have an inverter, the inverter can maintain a constant frequency and constant amplitude. So it can do a lot of good stuff. Here's another nice big storage system. And this is your lithium battery storage. Okay, and here's another storage system. This one, you notice the walkway around it. That's how you don't get your feet wet if one of these things leaks. This is one of those flow battery systems. I don't know how many megawatts it is, but it's a large flow battery system. And we're going to see a whole lot more of them. Their energy density isn't all that good, but the cost per kilowatt hour of storage is pretty reasonable compared with the cost per kilowatt hour of storage of some of the other systems. So here's a thing that Elon Musk did in South Australia. This is a 100 megawatt energy storage facility. Notice I say 100 megawatts. That means it will deliver 100 million watts. The question is for how long? Well, it will deliver it for 1.2 hours because it has 120 megawatt hour capacity. And this thing came on 140 milliseconds after a coal-fired power plant tripped off, and it stabilized the grid down there. So, and he built it in less than 100 days. And if you want to read about it, here's a nice reference for you, and another one here. All right. So I'm not necessarily advertising Tesla or Elon Musk, but this is one of the things they've done besides with SpaceX. They're out in the South Australian desert with the battery storage system to stabilize the grid down there. And they can charge up those batteries when there's extra, and then they discharge when they need to discharge. Okay, here's your pumping water uphill storage, pretty straightforward. It takes roughly half an hour to change the direction of water flow. So you pump up, and if you anticipate you're going to need some extra energy in a half hour, then you crank a few valves, and half hour later, the water's running downhill again and making electricity for you. Okay, and we talked about the designed initially to pump water uphill for nuclear. The major storage right now in the world is pumped hydro. It's big, all right? But other sources are catching up, and the economics of pumped hydro are kind of interesting. And one of the problems, of course, is permitting and construction. And generally, you're looking at 10-year time frame. And a lot of people are now just waiting to see what's going to come up that might replace the pumped hydro. But there's a lot of it out there right now, and it'll be there for a long time. A lot of repeat cycles possible. Flywheels, they're good for frequency regulation. Capacitors, great for transient voltage stability. Voltage across a capacitor cannot change instantaneously. Your electrical engineering professors drilled that into you, and you still remember it. I'm sure you do. Okay, and what about magnets? That's the current in a inductor cannot change instantaneously, so they're great for stabilizing current. All right, high power batteries, contingency reserve, electric vehicles. If you had 200 million of these things, or even 100 million of them that were parked at one time, and if each one had 5 kilowatts and 50 kilowatt hours available to the grid, that can solve a whole lot of peak loading issues. And then there's hydrogen, and the hydrogen folks are absolutely not going to give up on that. I sat in on a board meeting of the Florida Solar Energy Center, and they are still working really hard on hydrogen as a fuel by way of fuel cells, hydrogen as an energy storage mechanism. And so hydrogen, I think, is going to stay on the map, and it's probably at some point going to reach an efficiency level where it's competing. And maybe it's going to be a lot more cleaner to make hydrogen than to have to mine some of these rare earths. So look at hydrogen carefully, because that may be one of the game changers out there. Weightlifting, there's some very interesting things. Mostly in the European Union, where instead of lifting water, they lift weights. And mostly I think they're lifting concrete blocks. And somebody did an analysis on that, and they figured the number of kilowatt hours going into building the blocks exceeds the number of kilowatt hours you can store and return continuously over the life of the system. I don't know if that's true, but it's one of the things that's going on about those. And so again, it's the kind of analysis when you do something new, you want to do that, because if you don't do it, somebody's going to do it for you. There are microgrids. Once had a graduate student who did some very nice work, wrote a PhD dissertation on microgrids, and the utilities just thought that was a great idea, and they grabbed her up really fast. So what happens to the grid as a result? Well, here's what we've got now, mostly one-way stuff. We generate it, we transmit it through transmission lines to substations, where it gets transformed down to distribution level, and it goes to small loads, medium loads, and big loads. But it's mostly a one-way direction. Mostly, although there's been a lot of change in that lately. And here's what we're looking at, though. We're looking at big loads, small loads, medium loads. We're looking at baby PV, small PV, medium renewables, big renewables. You can look at the picture and digest that over dinner tonight. Okay, I think we are pretty close to being done, 4:05. We should be finishing. So let's see. Well, yep, that's the beginning of the story. We spent a little bit more time, like about 10 times more time on discussion today than usual. And I thank you very much, all of you, for participating in that, because it was very enlightening from my standpoint, and I'm sure that it was enlightening for others as well. And after all, this was supposed to be an interactive course, and thanks to you, you made it happen. So, is there any other comments that anybody might have, want to make? We'll say 2 more minutes, and then our host is going to want to shut down and start working on dinner. I see some things in the chat, but that should be between the chat and the host. Yeah, webinar video and other things. So that's for everybody to look at. I don't see any more Q's and A's. So in that case, I thank you very much for being with us this afternoon. Claim those 2 credits of live instruction. And who knows, you yourself may already be a part of this story. And at some point, you just may become a part of the story if you're already not a part of it. Some of you are part of the story just because you own electric vehicles and so forth. When you get to designing stations and whatever else, I can tell you it's a good feeling to go to bed at night knowing that you've signed off on 150 kilowatts of residential solar. It makes me feel like maybe I'm helping my great grandson as far as where he might be when he turns 80 in the year 2100. A couple more Q's and A's there. Okay, thank you, Edward and Majid. You're very welcome. I hope you benefited from your participation this afternoon. And I hope everyone else did as well. If nothing else, I hope you all had a good nap, or whoever needed one. And have a good holiday season, everybody. Okay, Mr. Host, I believe we are all set here. I'm going to stop sharing. And oops, another chat here. Let's see what we got. Oh, that's a chat. Missed the wrong one. Q's and A's. And Kenneth and Anonymous and Mindy, you're very welcome. Appreciate you taking the time, because I know most everybody, if you're half as busy as we are, you're working some pretty long hours. And taking the time out to, and I also know that you have to do this or you can't renew your license. But I hope you felt it was worthwhile. And once again, I thank all of you for all of your well-thought questions, and also appreciate some of the answers that I didn't have that you were able to provide. That just enhances the whole program, and much appreciated. Okay, Mr. Host, I believe you can turn off the recording machine now.